So this is just a matter of using definitions. RIP points from the wire segment to the point P, and so it points this way. The delta L vector points parallel to the wire and in the direction that the current is flowing, and so it points this way. Now just use the right-hand rule for that cross product of delta L and RIP, and you will get that the B field points into the page, which you could also get using the right-hand rule for current that you've known for some time now. So let's see an example of using the Biot-Savart law. So I've written the Biot-Savart law out right here, and let's use it to find the B field due to a straight wire. But notice this is now not a long straight wire, in other words, not of infinite length, it's of finite length. And so here's a point P, some distance r away from the very middle of this wire, perpendicular out from the middle, and I've set the current direction, and the first thing I'm going to do is I'm going to break the wire into bits. And what I really mean is I'm going to pick an arbitrary piece of wire and define the delta L vector along that piece of the wire. And so that now sets an RIP vector, and note that the RIP hat is just the unit vector in that direction, and that also defines our angle theta. It's right here. And so notice, if you use the right-hand rule, you will see that delta L cross RIP hat is into the page. So I've set x and y this way, so the z vector is coming out of the page. If you do that delta L cross RIP with the right-hand rule, you're going to find that this vector is into the page, or in other words, delta L cross R is going to be delta L, no longer a vector. RIP hat magnitude is 1 sine theta, and this is all in the negative k hat direction. So now I can rewrite and I'll note this is really a theta I. And I'm not going to worry about the direction anymore. I now know which way it is, and so I'm just going to take absolute values of all of that and drop the k hat. I know the direction. So we would like to get this all in terms of one variable we can integrate with respect to, and the key is going to be to look as usual at geometry. Here's a triangle that'll be useful to us, and I'll note that this angle is 180 degrees minus theta I, and if you know your trig identities, you'll know that sine of theta I is the same as the sine as 180 minus theta. And notice that the sine of that angle, so sine theta I, is going to be opposite over hypotenuse, or r, over RIP, and so that removes my theta I from here. I'll end up with an r, and this will now be an RIP cubed in the denominator. And the triangle also tells me that if I call this distance right here yi, and finally, delta Li is just a little step in the y direction. And so, in fact, we might as well just call it delta y. And so now I'm left with y as something that's appearing everywhere that I'll be able to integrate with respect to, and I can write the whole thing in terms of that. Finally, I can integrate. I'm taking a sum of this and taking the limit so that my b is just an integral, and that is going to be from negative L over 2 to L over 2, and all the constants will come out front. And all I have to do now is an integral. I've carried out the integral. It's a trig substitution, a lot like some that we've seen earlier in the course, or just plug it into Maple, and it comes out like this. And I'll note that in the limit, as L goes to infinity, in other words, as we're looking at an infinitely long wire, then we can ignore the r squared in here, and this just becomes 2 over L. And so the L's cancel, and there's a 2. And so this whole thing goes to mu naught I over 2 pi r, which is exactly what we saw for an infinite wire from Ampere's law. A useful result we can now get with things we know is the force between two current-carrying wires, and we'll restrict our attention to the simple case where the wires are parallel with each other. And furthermore, we're only going to think of situations where the wires are very long compared to the distance between them, because then we can treat them as infinite wires. Otherwise, we get into some very complicated calculations indeed to deal with how things work at the ends of the wires. So let's look at two wires with currents going in the same directions, separated by some distance s. And in this picture, if you think about the B field due to wire 1 at some location on wire 2, you'll see that the right-hand rule tells you it should be into the page. And so then the other right-hand rule tells you that the force that wire 1 is exerting on wire 2 must be towards wire 1. So this is an attractive interaction. Note that Newton's third law tells you the force that wire 2 exerts on wire 1 must be down towards wire 2. So now we have an expression for the B field due to wire 1 at the location of wire 2, and we have an expression for the force that wire 1 would exert on wire 2, where, note, you have to be careful that in there that is the current in wire 2 and the B field due to wire 1, and put those all together and you have an expression for the magnitude of the force that one wire is exerting on the other. Part of the reason it's useful to be aware of the force between two current-carrying wires is that the official definition of the ampere is in terms of it. So here I have copied the official definition directly from the website of the Bureau International des Poids et Mesures, and it says that the ampere is the constant current which, if maintained in two straight parallel conductors of infinite length, placed 1 meter apart, would produce between those conductors a force of 2 times 10 to the negative 7 newtons per meter of length of the wires. So we're working in terms of this expression that we have, except we're talking in terms of the force per unit length. And then if you just think of setting both of those currents to 1 ampere and the distance between them to 1 meter, and set that force per unit length to the required 2 times 10 to the negative 7 newtons per meter, you see now why mu naught is a precisely defined constant, because it is defined by the definitions of the ampere, meter, and the newton. Here's another example, but I'm going to go through it very quickly because it's a lot simpler than the straight wire. Let's look at the B field at the very center of a current loop. And so note, first of all, that no matter where we're looking here, the delta L vector and the RIP vector are perpendicular, and so the cross product just comes out to the length of the delta I vector, and with the axes I've set, it's in the k-hat direction. So with this current in this direction, the B field at P is up along the z-axis, and so now I won't worry about direction anymore. And then also, if I define this angle phi I, which is just an angle defining where I am on the loop, then I can rewrite delta Li just using the definition of angles in radians as r delta phi, where capital R is the radius of the loop. And note that the magnitude of RIP everywhere is just r. And so that makes writing out the Biot-Savart law very simple. That cross product becomes a very simple expression. The denominator is just a constant. And so now this integral is going to be very simple. Once we write it all out as an integral, it's just going to be with all the constants out front. Well, check your understanding. As usual, it's the directions that are difficult, so here's something for you to practice thinking about the directions. There's a rather odd-shaped loop of wire and a point P nearby, and work out which way the magnetic field is at that point P.